What is a fluid? A fluid is something that flows. What does flowing mean? Let's take this example. There are two flat plates shown hatched, on between which there is a green substance. The lower plate is fixed. On the upper plate, we apply a force F1. If the green substance was a solid, then the upper plate would move under the action of force and will come to a stop after a while when the green substance now has been shown in a brown color, and there is the angle from 90 degrees has reduced to an angle theta 1 less than 90 degrees. What does it mean that there is no more motion of the upper plate when the force F1 is applied? That force F1 must have been overcome by some internal force produced in the solid. This internal force is the shear force. If we applied more force, a larger force F2, then the plate will again come to rest but with more distortion. Now the angle will reduce to theta 2. That means when we deform a solid in shear, a force builds up to oppose the deformation, and that force depends upon the deformation. More the deformation, the more is the force. In earlier case, the opposing force was F1. Now the opposing force is F2 with more deformation. So more the deformation, more is the opposing force. Now, if the substance, the green substance, was not a solid but a fluid, I marked two lines. When you apply a force F, the upper plate never stops. It keeps on moving. And ultimately, it accelerates first, but ultimately it acquires a velocity v. What does that mean? The upper plate keeps moving and the fluid keeps on deforming. No equilibrium state, but an equilibrium velocity v of the plate. The equilibrium velocity v increases as the shear force F increases. This means that mere deformation of fluid does not build up resisting forces. Since there is an equilibrium velocity, more the velocity, larger the force, a resisting force is developing for sure. The resisting force is thus dependent not on deformation but on the rate of deformation. A fluid does not resist shear force by acquiring an equilibrium strain. We define a fluid as a fluid deforms continually under the action of a shear force, but at a rate determined by the magnitude of the shear force and the fluid properties. A fluid at rest or in uniform motion, when there is no deformation, cannot sustain any shear force. This we use as the defining statement of a fluid, as a definition of a fluid. A fluid at rest or uniform motion cannot sustain any shear force. A relative motion of fluid is necessary to develop any shear force. When a fluid is in motion, there may exist shear forces as well. Let us consider the rate of deformation. Again, we have the same setup as before. We have a green fluid. On the green fluid, we have marked two lines at right angle to each other. One a horizontal line segment and one a vertical line segment. this fluid is moving. You would know later on we will do that the fluid have a property with which we say that there is no slip between fluid and the nearby wall. So fluid at the stationary plate would have zero velocity, would be stationary, and fluid adjacent to the moving plate would be moving with the velocity v naught, the velocity of the plate itself. And the higher we go, more is the velocity, lower the velocity is lower. So after a time delta t, upper end of the vertical line moves through a larger distance than does the lower end of the vertical line. So that the location of those two black lines would now be this. So the angle between these two lines have now decreased. What is the decrease in this angle? This decrease is gamma, called the shear deformation, and you would see by simple Taylor series expansion that this would be given by delta Vx over delta y into delta y dt. So this is the additional distance that the upper end of the vertical line has moved over the distance moved by the lower end of the vertical line. So the angle gamma, which is the deformation in delta time delta t, is delta Vx by delta y into delta t angle. The additional deformation divided by delta y would give you this. And then since this is the deformation delta t time, so in unit time or the rate of deformation is delta Vx by delta y. There is a famous law of viscosity, the Newton law of viscosity, which you must have done in your high school, which states the shear stresses in fluids are proportional to rates of shear strain. The rates of shear strain, not the shear strain itself, but the rates of shear strain. So that tau is proportional to gamma dot, the dot representing the differentiation with respect to time, delta gamma by delta t. And we just shown that gamma dot, the rate of deformation, shear deformation, the rate of shear strain is dvx by dy in the case discussed. So for the parallel plate geometry shown earlier, tau, the shear stress, is proportional to delta Vx by delta y. Or introducing the proportionality constant mu, tau is equal to mu delta Vx by delta y. The proportionality constant is termed as the viscosity and is the material property. Now this is a very famous relation, but the applicability of this is not universal. In fact, there are whole classes of fluids which do not obey this law. So the fluids that obey this law are called Newtonian fluids. Newtonian fluids are those fluids which obey the Newton law of viscosity with a constant mu. On the other hand, the fluids which do not obey this law are termed non-Newtonian fluids. We can look at the dimensions of viscosity. Since tau is equal to mu dvx by dy, So dimension of viscosity would be dimension of shear stress divided by dimension of V by Y. The dimension of viscosity are force divided by L square, and we get the dimension of mu in MLT system as M L minus 1 T minus 1. The units are correspondingly kilogram per meter second, which also is Pascal second, which is derived from this. This is second and FL minus 2 is Pascal. So Pascal second. The other unit is a poise. Poise is a unit which is equal to 10 raised to minus 1, 0.1 Pascal second. A most commonly used units in fluid mechanics is the centipoise, which is 1/100th of a poise, which is equal to 10 raised to minus 3 or millipascal second. And why is that used? Because viscosity of water at room temperature is about 1 centipoise. Something easy to remember. And centipoise is 10 raised to minus 3 Pascal second. Pascal second is the SI unit which you would be using in all your problems that you do in a course in fluid mechanics. But quite a bit of engineering literature, the viscosity is given in centipoise. There is a wide variation of the viscosity of air. Has a viscosity of 0.0185 centipoise. For gasoline, it is 0.29 centipoise. For water, as we just said, is 1 centipoise. Mercury is a little more viscous, 1.55 centipoise. And the SAE 30 motor oil that you use in your cars typically is 440 times the viscosity of water. 440 centipoise. Very viscous. Glycerine is also a very viscous substance. Effect of viscosity. What does viscosity do? Again, we have similar geometry, two parallel plates with a fluid in between. But in this case, we have the upper plate stationary, just for the convenience of my drawing, that's all. And the lower plate is suddenly start moving at a velocity v naught. Initially, this was all stationary, so the whole fluid was stationary. At time t is equal to 0, the lower plate is set into motion with the impulsive velocity of v naught, suddenly given a velocity v naught. So what will happen? Because of the no slip condition that I discussed just a little while ago, the fluid in the immediate contact with the lower plate starts moving immediately with the velocity v. The fluid adjacent to it is still stationary, so this gives a velocity gradient, which is negative, of course, the velocity decreasing in the upward direction. And so that creates a shear stress. Because of shear stress, the fluid adjacent to this adjacent fluid starts moving slightly. And after a little time, you might get a velocity profile which looks like this. This reddish line shows you the variation of velocity in the vertical direction across the fluid after a little time delta t, a time after the lower plate has set into motion. You see, after a few units, the fluids in the upper layers has not moved at all, has not started moving at this time. Now this has set a velocity gradient again, so there would be more shear stresses, and because of which the effect of the lower motion will penetrate upwards, and we will, after a little more time, we might get a velocity profile like this. and then like this, and then like this. After a long time, we would get a velocity profile which would be straight. We will later on in the course that mathematically we will obtain a straight line profile between the plate. This is the profile that you used in your high school between two parallel plates. You call this flow a Couette flow, a steady state flow after a long time. What is happening? The effect of the motion of the lower plate is diffusing upward. Diffusion is the word. We say the momentum. Later on we'll use another word, vorticity, is diffusing upwards. Penetration and the effect of motion of the bottom plate due to action of viscosity penetrates upwards. This is the effect of viscosity. The penetration increases with time. Action of viscosity is like a process of diffusion. The viscous action of the fluid resists the motion of the lower plate. At this steady state, the fluid attempts to drag the upper plate to the right. There would be shear stress on the lower plate in that direction. So we need to apply a force constantly on the lower plate to keep it moving. Not only this fluid would apply a shear force in that direction on the upper plate. So we'll need to apply a force on the upper plate in the opposite direction to keep it stationary, to overcome this effect of drag on the upper plate. We'll have occasion to calculate these forces and discuss more later on in the course. A rudimentary viscometer. How do we measure viscosity? We have two drums, an inner drum and an outer drum, or cups. This is, I'm showing the top view of the two cups. There's a fluid in between the two cups. The inner cup is rotating. Because of the viscous action, there would be a force that would develop on the inner cup which we'll need to apply to keep it moving, or a force that we need to apply on the outer cup to keep it from rotating. We measure that force. The picture between the two cylinders, two cups, look like this. The velocity there is omega r. The gap d, the velocity on the stationary cup, is 0. You can know the velocity gradient. So we assume linear velocity in the inner cup. We calculate the velocity gradient. From velocity gradient, we find out the shear stress by applying the Newton's law. Then we find a force on a small element like this. We find a torque of this small element by multiplying by r, the radius, and then integrate to find out the total torque that we need to apply to keep the outer cup from moving. We can measure this and relate it to mu, and that is how the viscosity is calculated using this rudimentary viscometer. We will do this problem later on in the course. I have included here just to give you a flavor of what kind of calculations are moved. Probably you have done this problem in your high school as well. Classification of fluids based on stress-strain relationship. You see, in this solid there is no rate of strain, just strain, and we have a shear force. For an ideal fluid, non-viscous, if viscosity is 0, we can have any shear rate of strain and there will be no shear stress. For a fluid that we discussed, a Newtonian fluid, there is a linear relationship. Mu is constant, shear stress is mu times rate of strain. But there are other kinds of fluids. A pseudoplastic or a dilettante in which this is not a straight line. These are all not Newtonian fluids. Or we may have a plastic in which up to a given level of shear stress there is no rate of shear strain, but then you can develop any rate of shear strain after that for the same stress. We have fluids that have a threshold, and beyond that you need more shear stress to get a rate of strain. These are known as Bingham plastics. In this course, we would largely, or we would essentially discuss Newtonian fluids only, though within this lecture I'll give you some examples of Bingham plastics. You see, a rod is rotating in a fluid. You can see these two pictures. These are GIFs. The fluid is rising up the rod, and when a big bulb is formed, it collapses down and starts climbing again. In a Newtonian fluid, inertia would dominate and the fluid would move to the edge of the container away from the rod. Centrifugal action. But however, the elastic was generated by the rotation of the rod, and the consequence is stretches of the polymer chains in the solution that we are using here results in a positive normal force upward. The fluid rises up the rod. The bulbous shape remaining at the end of the video is more onset of instability as the mass that has been forced up the rod relaxes and overcomes the force pushing it from below. The rod climbing effect. Another non-Newtonian effect is the die swell. You see, if the Newtonian fluid was flowing down a die, flowing down a hole, it would follow a contour like this. It will accelerate, and because of acceleration, the cross section will decrease because volume flow rate at any two cross sections is the same. So if the fluid is accelerating downwards, then downwards the cross sectional area would have been small. But you use polymers like a 2% aqueous solution of polyacrylamide. The fluid swells after coming. Fluid swells means its velocity is decreased because of being pulled up by a normal force. There is a third non-Newtonian effect that I want to show you, and this is very interesting. An open siphon. Again, this is because of this. Polyethylene oxide, 5.5% solution of polyethylene oxide, a polymer. You start the flow, and because of tension, because in this, the fluid, the beaker empties itself. That brings us to the end of this lecture. In the next presentation, we'll discuss fluid flow phenomena. Thank you.